In this lecture, we're going to discuss powers, exponents, and the exponential function. So first of all, let's specify that we're going to work with the sets of natural numbers. So the set of natural numbers is denoted by this n with a double line. Sometimes people put a double line on the middle segment there. But so these are the whole positive numbers. Then we have the set z of integer numbers. Here we include 0 and the opposites of the natural numbers. We have the set q of all fractions. So these are numbers that can be written as a over b, where a is natural. Actually, a is integer. The numerator can be 0, negative, or positive, and b is natural. And finally, we have the set of all real numbers, which is pretty much all numbers we work with. I'm not going to give it a definition. Actually, it's a very, it's a somehow somewhat fine matter to give it a precise definition, but these are all the numbers that we're going to use. And let's specify that real numbers that are not rational, are not fractions, in other words, with integer numerator and denominator, not in Q, in other words, are called irrational. A very nice characterization of irrational numbers is that a number is irrational if and only if its decimal expansion does not start repeating at any point. So say alpha is irrational if and only if its decimal expansion does not start repeating at any point. What I mean with this is that let's say you have this number 4.1769, and then all of a sudden it becomes 73, 73, 73, 73, and continues like that. So this number will be rational because its decimal expansion starts repeating at this point. And when I say repeating, means you have a specific segment, 73 in this case, which appears consecutively. And we can easily write down a number where you can see there is a pattern. We can guess what the digits are, but there is no repetition of the type that we just described. So for example, take 0.12, 122, 122, 122, 22, and so on and so forth. So this number here, even though you can easily guess what its digits are, however, since it has longer and longer strings of twos, certainly it never starts repeating. So this is an irrational number. Okay. So now, also I should say at this point that maybe the most famous irrational number is the square root of 2. So this is an irrational number. What is the square root of 2? It's so x is equal to square root of 2 if and only if x is greater than 0 and x squared is equal to 2. So that's what we mean by the square root of 2. In general, we can define nth roots of positive numbers. So let's say that a is positive, then the nth root of a is the number x, which is such that x to the nth is equal to a. So we should here give some examples. The cubed root of 8 is 2. Why? Because 2 to the third is 8. The fourth root of 81 is 3. Why? Because 3 to the fourth is 81. And the fifth root of 32 is 2. Why? Because 2 to the fifth is 32. And I have already implicitly used the first definition that I would like to give. And the very first definition for exponents that I would like to give is that a to the n is defined to be a times a times a n times. So this is how we define the simplest type of power. Again, we already gave some examples. So in the parentheses here, you can see all these are examples of this definition. So take the last one. 2 to the fifth is 32. Why? Because 2 times 2 times 2 times 2 times 2, I hope I give the right amount of 2's, is 32. Now, it's interesting to notice here that there are two properties that are of great importance. And those properties are that a to the n plus m. So when you have an exponent which is the sum of two natural numbers, then you get the product of the corresponding powers. And a to the n all raised to the mth power is a to the n times m. Okay, so we have these relations, and now these relations are the basis of what one wants to do. So we want to preserve these relations and simultaneously allow the exponent to be first integer, then rational, and eventually real. So we're asking ourselves, how is that possible? And here are the definitions that we give. So first of all, let me just notice here that a here, the base that we're going to be talking about, is going to be a positive number, and usually you will see, especially when we need that condition, usually a is different from 1. Why different from 1? If you use 1 as your basis, you keep getting the same number always. 1 raised to any number, any real number will be 1. So it's not such an interesting function. So let's start with what a to the 0th power is. It's not hard to see that the only possible choice for a to the 0, if you want to have the two properties that I gave you before, is equal to 1. I mean, think about it. I wouldn't like to go over all the details here, but this is rather simple. It's because a to the 0 is the same thing as 0 is 0 plus 0. So by the same property, that would have been a to the 0 times a to the 0. And you see that a to the 0 is a to the 0 times a to the 0. If you cancel a to the 0, assuming that it's non-zero, because if it's 0, then everything should be 0, but we know that that's not true. So a to the 0 has to be different from 0. And by a simplification, we get that a to the 0 has to be 1. And this is the very first definition that one does. So raise any positive number to the 0th power, and what you find is 1. The next definition has to do with integer power. So raise a to the negative n, and you get 1 over a to the n. So for example, let's give some examples here. So what would be 2 to the negative 5? 2 to the negative 5 would be 1 over 2 to the 5, or to the 5th, if you will, which is 1 over 32. And what is 3 to the negative 3? This is 1 over 3 to the 3rd, which is 1 over 27, and so on and so forth. Okay, so you get many interesting examples in this respect. So our next goal is to define a to the 1 over n. What is a to the 1 over n? This is where it gets kind of interesting. A to the 1 over n is defined to be exactly the nth root of a. Obviously, if n is 1, the first root is by definition the number itself. And if n is 2, it's the square root. So again, it might be a good idea to give some examples. However, we have to choose our examples very carefully. Otherwise, we cannot really compute the corresponding roots. So for example, I can tell you what a to the 1/3 is. A to the 1/3 will be the cubed root of a, which is the same thing as 2. I could tell you what 125 to the 1/3 would be. That would be the cubed root of 125. Think about it. What number has third power 125? The answer is 5. Or I could tell you what 64 to the 1/6 is. So that would be the 6th root of 64. What number do you need to raise to the 6th power in order to get 64? And the answer is 2. Okay. And this brings us to rational powers. So if we have a rational power, so let's say that we have a to the m over n, we could define it in 2 different ways. So we could say that this is take the nth root of a and then raise it to the mth power, or take the mth root, the mth power of a, and then take the nth root of that, so raise it to 1 over n. Both things are going to give us exactly the same one, but for most computations, especially if we can find a simple number, the first option is the better one. So for example, let's say that we want to compute a to the 2/3. Then this is 8 to the 1/3 all raised to the 2nd power, which will give you 2 to the 2nd power, because a to the 1/3 is 2. And this is 4. Or let's do another one. So how about 27 to the 4/3? Why don't you pause the video and try to compute it? So 27, I said 27, I wrote 24, apologies. So how much is 27 to the 4/3? So this is going to be 27 to the 1/3, all raised to the 4th power, which is 3 raised to the 4th power, which is 81. Okay. And these are 2 simple examples. Actually, let's do one with a negative power. So how about 4 to the -3/2? Again, pause the video and try to compute this. How much is this going to be? So what you want to do is 4 to the 1/2, all raised to the -3, which is going to give you 2 to the -3, which is 1 over 2 to the 3rd, which is 1 over 8. Okay, so you can play around with this type of examples. The only time that you have to be a little careful is when you have fractional powers. Unless it's a root that you can easily find, it's not going to be a rational number, and it's going to be very hard to play with them. The bottom line is that as long as you use this definition, all the properties of the exponential function remain intact. Now, what I would like to do at this point is discuss a very interesting issue, which is what happens if we want to raise a number to an irrational power. So let's say that, for the sake of the argument, that we would like to define 2 to the square root of 2. Now, I told you that square root of 2 is not a it's not a rational number. It cannot be written as a fraction, so we cannot use the previous definition. However, square root of 2 has a decimal expansion. And one way or another, now I'm using the internet in order to get that decimal expansion. And you can see that square root of 2 is approximately equal to 1.41421,356, and it continues. So in other words, square root of 2 is approximated. The first very rough approximation of square root of 2 is, of course, 1, which is a fraction. It's 1 over 1. Then the next one would be 1.4, which as a fraction is 14 over 10. Then you have 1.41, which is 141 over 100. Then you have 1.414, which is 1414 over 1,000. Then you have 1.4142, which is 14142 over 10,000. Let's write one more, 1.41421, which would be 14141 over 100,000. The point is that all these numbers that I wrote here, the approximations that is, are irrational, are rational numbers, they're fractions. And I can compute, again, with the help of a calculator. So 2 to the first, of course, is 2. I don't need a calculator for this. How much is 2 to the 14 over 10? So 2 to the 14 over 10, this is where I'm going to use my computer. In fact, the funny thing is you can even do a Google search. And it turns out that 2 to the 14 over 10 is 2.63901, and it continues. And how much is 2 to the 141 over 100? It turns out that this is 2.65737, and it continues. And how much is 2 to the 1414 over 1,000? It turns out that this is 2.664749. And how much is 2.14142 over 10,000? And this is going to be 2.665119, and so on. And the last one, which is 2.14141 over 100,000. You can actually continue to play this game, and especially with the powerful calculators that you can even find on the web nowadays. You can find more and more. And now, here's what I want you to understand, that as you look at this thing here, you will see that certain decimal digits start stabilizing. So for example, you can guess that, you see, the integer part is the same for all of them. It's 2, right? Now, also you can see that the 6 never changes. So you can argue that it stabilizes, and it's 6, the first decimal digit after the point. Now, for the second decimal digit after the point, you can see that you start with 3, then it becomes 5. But once you get to 6, it never changes. So you can argue that this has stabilized. And maybe it's also a good guess that the third decimal point after the third decimal digit after the point is 5. So you might argue here that at least the first few digits of the number 2 to the square root of 2, as they emerge from the computations that you can make, are equal to 2.66 5, and it continues. And of course, if you want more decimal digits, you may have to check out more or closer approximations to the exponent. The bottom line is that this way, eventually, we can define. So if a is greater than 0, and usually a is different from 1, we can define the function f of x to be equal to a to the x as a function on all real numbers. So this is going to be the exponential function with base a. And these functions usually grow very, very fast. So just to give you an idea of what their graphs would look like, it depends actually on whether a is greater than 1 or less than 1. So if a is greater than 1, you see a pretty rapid increase. And if a is less than 1, then you see the other way around. It's a very rapid decay, or something along these lines. You can use a graph calculator if you want to see more precise pictures, or you can check the web, but this is what pretty much they will roughly look like. One interesting question that comes up now is, out of all the different bases, which one is the most useful? And the most useful base? And the answer is very, very surprising. Turns out that it's not the number 2, it's not the number 3, it's not the number 4, it's not something you would normally expect. Unless you've seen it before, you would never guess it. It's so the most useful base, I should say, the most useful base is actually this number, which is denoted by e. And if you want to precisely give this number, one way to precisely give this number is that this number is this infinite sum. It's 1 over 1 plus 1 over 2 plus 1 over 6 plus 1 over 24 plus 1 over 120 plus 1 over 720. Maybe you haven't realized what the pattern is with these denominators, but there is a pattern. And what you have here is the so-called factorial. So it's called factorial. And basically, n factorial is 1 times 2 times all the way to n for any natural number. And we also define 0 factorial to be equal to 1. So this is the same thing as 1 factorial, 2 factorial is 2, 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4, which is 24. And this is 5 factorial, and this is 6 factorial. And this is pretty much the number e, and it keeps going. It doesn't stop. This sum is, as we say, an infinite sum. Another way to look at the number e is that e is the limit as n tends to infinity of 1 plus 1 over n to the n. What does that mean? We do have a situation which is very similar to what we were just discussing. So if you take for n equals 1, you will find 2 to the first all raised to the first power, which is 2. If you take for n equals 2 and substitute n equals 2 in this formula, you will get 3/2 squared. If you get n equals 3, you will get 4/3 to the third power. Then you will get 5/4 to the fourth power, and so on and so forth. If you compute these things, you will see that little by little, the decimal digits of the number e merge. E is approximately 2.71828, and it keeps going like this. And obviously, the obvious question in all of this is, why in the world does this happen to be the most useful base? And we're going to answer this question, but not right now. We're going to answer it by using calculus tools a little later. So for the moment being, let's leave it as a small mystery why, out of all the different numbers that you could use as basis for the exponential function, this very, very strange number that we have no clue where it's coming from to begin with, happens to be the best choice. We will leave it at that. Thank you for watching.